questions, we will be asking your name on them because it helps us later on when we bring them into Slack and upvote and downvote for the questions that you like. Jonas, you can take questions as you go if you want. It's up to you. But we can keep an eye on taking them at the end to allow people to upvote and downvote. So yeah, Jonas, you can take it away.
Okay. So welcome everyone to this tutorial about zfit and hepstats. So this tutorial is going to be a walkthrough to the main components of zfit. Zfit itself, if you haven't heard of it, is a model fitting library which is written in pure Python and uses TensorFlow as its backend. zfit itself, though, is limited in its capability that it does only model fitting and sampling, basically. We see here these 5 parts that it cares about, basically building a model, getting a data, creating a loss out of it, give it to the minimizer, and minimize it, for example, like log likelihood, minimate and stuff, and we're getting a result. It is on one hand very strongly integrated into the whole PyHEP ecosystem and affiliated with it, and as we will see, it wouldn't exist without all the packages there, like iminit and uproot. And furthermore, it also relies on hepstats, for example, which is built on top of zfit to do statistical inference. This you will also see in the tutorial at the end. Furthermore, if we go now through the tutorial, keep in mind that we're in Python, so zfit doesn't try to solve every little problem. Very often, as you will see, we can just write 1 or 2 lines of Python code, and we do stuff that otherwise we are used to have a function for that. So the first component that we have here is the data. We can do all the imports, and the idea of the data and the space is that it just can be loaded and is in a unified format inside zfit. So there isn't a lot that has been done, like all the pre-processing, for example. This does not belong to zfit, but we have pandas, and we can also convert, if you have it in zfit, into a pandas data frame, back and forth. We can use uproot directly and do all the pre-processing there. So this is really just to load in to the zfit format where we can have root or numpy or pandas, anything basically, or even tensors. Now, if we want to do a model fit, we want to build our model and fit that, one of the things we need is to define our data space. So, contrary to other libraries, in zfit, the space for the data, which we feed in and is normalized, and the parameters that parameterize your model is quite a distinct thing. So if we define now here our observable, we have one observable, ops1, and this is defined within the limits -5 and 10. This space object has a few nice things that we can read here. It can calculate the area, it can give you back whether an event's inside or not, it can filter things, and we can also do more arithmetic with those spaces. For example, we can have multidimensional spaces. We can just multiply them, we can have distinct regions that we can add and so on. We'll go into more details in a few later tutorials on certain aspects, for example, multidimensionality. For this tutorial, we'll just go into, let's say, intermediate level of different parts. So, for example, to load into zfit, all we can do is we create now with numpy some data set, some random data set, and load that into zfit. Now we have this data normal set. The data sets, they don't have a lot here, they just have like how many events do we have in there, how many observables, like what's dimensionality, and maybe weights if we want that. We can also retrieve a smaller data set of a larger one, let's say higher dimensional, if we ever want that. And we see dimension 1, and the observable that we've given, we defined is in -5 to 10, so we now cut out all the events that are higher or lower than this, which usually we want if we want to fit in a certain range. Now, building models, that's the largest part in zfit itself, which mainly consists of PDFs that are normalized over a certain normalization range, and they are provided by a class. A model itself is parameterized by a parameter object. As you can see here, we can create a certain parameter object like this. The syntax probably looks already similar to you. We have an initial value, we have a lower, and we have an upper bound. We can give a step size, which is sometimes good for fitting, which is roughly the standard deviation. We can say whether it's floating or not. So just because you don't set limits doesn't mean it's not floating. And we can also change its attributes, of course. Now sigma is first floating, and we can change that So it's not floating, and then we can change it to floating. One very small thing here on the pitfalls and notebooks, these parameters are unique. So we cannot now create a new parameter, which is also called mu. This is a new unique identifier, because if you do your fit afterwards, you want to know which name corresponds to which parameter. So we cannot create a second mu, which is different for a space. We can define a different space because we want to have different range and so on. They will then just match. So to create, for example, a Gaussian, which are simple, we just define observables that is defined in our mu, our sigma. Then we have our model, which again contains some information. How many observables do we have? What are the observables that we are in? What is the space, the default limits that we use it? This is, for example, used for integration or for sampling. And the normalization range, which is by default also the default space. This is the range is normalized over, but we can also say set norm range and define this differently. It's an advanced feature, but we can do that. The parameters that describe this shape are stored in gauss.params, as you can see here, and there's a dictionary which has just mu and sigma, two strings matching the parameters. These are the names that are not the names of the parameters we've seen before. Sigma was called sigma 42 here. The name is sigma 42 and the byte name is sigma num. So they're called mu and sigma because every Gaussian has a mu and a sigma, let's say. We have a second method, which is get params, and this is more useful if you just want to get all the dependents. So, for example, if you now build the Gaussian which has just two parameters, and we say params, then it would give us mu equals to mu and sigma equals to the mu. But if you say get params, then it automatically gives us all the dependencies and doesn't duplicate things and so on. So the latter is very useful if you want to like determine what does it depend on. And the first one is good if you want to know the shape of it. The main functionality of a model is the PDF and the integrate and sample functions. As we can see, we can just use it like that. We can say what are the limits. We can also say what it should be normalized about. And this is now to sigma integration of a Gaussian. What we see here, by the way, this object that is returned is called a TF tensor, but this is basically just a wrapped NumPy array. As you can see here, if we just call, for example, NumPy square root on the integral, it just takes us the square root of it and we get NumPy array back. So it's very close already to a NumPy array. We can always do a zfit run on an object and we get for sure a NumPy array. We can also sample and we get back a sample data object in zfit. We can unstack it so we get the values out of it. And this again is a data object as we've seen before. We have observables and we have the dimensionality, and we can also use this sample now directly to get the PBF probabilities out of that PDF. Now, if you have this PDF, we may want to do some plotting, and plotting is just matplotlib. What we're doing here is literally just getting the lower and upper bounds, doing a lint space, and put this X into the model and get the Y. We do just certain normalization stuff so that we can also plot the data next to it, and then it just looks like this. This is now not fitted, of course, it doesn't match visible afterwards. But this is just simple matplotlib usage. Now we've seen a Gaussian, and zfit offers quite a few different models that are implemented. There are also some more in zfit physics, for example. And the Gaussian is nice, but we want to now do a real physics case. Let's say we want to have a signal component with a crystal ball, an exponential, which is a combinatorial background, and a kernel density estimation. Therefore, we define, again, our observable. We define our signal component, which is, again, we get all the three parameters, and we create a crystal ball. We say it's in its observables. We create our combinatorial background, which we do an exponential. And we create KDE, which just takes some data, and we just invent some data here from NumPy. There are a few different bandwidth that we can give. We can give also fixed numbers or parameters, but we do this adaptively, which usually is the best result. Now that we have the three models, we want to compose them together with the sum PDF. And when you sum PDF, if you have three models, we usually need n-1 fractions, because the last fraction is 1 minus the sum of the fractions, which we actually do here. We can also give in n fractions, in which case every fraction will be matched to a model, but then the normalization is completely up to us. And we have to make sure that all these fractions are normalized properly. The sum is normalized to 1. So what we can do, we've seen already, we have these parameter objects, and now it can be useful to change value of those. We can set it just like sigfrac.setValue, or we can even use a context manager, in which case it sets it back again. Which can now be nice, because what we can do is we have this complex model now. We have this sum that we build up here. And now we want to create some data, some sample data to have something nice to plot on, which we can do here. And since we want to set the values slightly differently than we set them initially, otherwise it's a little bit too easy to fit, we can just say, instead of a single parameter, we can say here, set values, and set this value to these values. Then we're inside, we sample 10,000, and we're outside again, it's set back. So now we can also plot this. This is the sampled one, and this is the PDF above. Sure, the PDF now is, if you have a composite PDF, looks not so nice, but this again is very easy to do because it's very transparent. So we can just iterate through our model, which has fractions, and plot each one with a certain fraction. So this here is the old plotting function to plot something composite. And then we got all the components. No magic, no slices, no fancy stuff that we need. Another thing are extended PDFs that we will be interested in if we do our fit now. An extended PDF is basically in zfit the same as a normal PDF. So if you make a PDF extended, you can either create one, like copying and setting it, or making it extended in place. If you do that, then nothing changes. So it's very important. It just behaves like it. It just has 1 or 2 functions that we can have additionally. It has an additional new, but behavior is exactly the same. So what we can do is we can have our model and we can create an extended model like this. Now we could fit this extendedly. But what we could do as well, which we didn't do before, but we can do that now, is actually taking our signal, combinatorial background and partial reconstructed background, and make all of those extended. Now we have some special feature. Let's say if you have a sum and every PDF is extended, then and only then we do not need the fractions. So we get now our extended sum model. Next is up is a loss. We want to here build an ambient loss. We can, for example, just take the Gaussian and the normal data, and we can get the value of our loss by calling that. And we can also transparently access the model, the data, and any constraints, which we will see later. And as well, we can get all the parameters from the loss. Now, if we want to create an extended loss, so if the absolute value of our model will be taken into account and fit to the species that we have in the number of events in the data, we can create it like this. And now this is our extended ambient likelihood, and we have quite a few free parameters. Now, for the minimization, there are a few minimizers built in, but most often Minuit is used and it's quite stable, thanks to the iMinute package. We first create a minimizer, and it usually just has a state, and then we can just fit it. What we can do here is we can first prefit now the right-tailed exponential, which we can do by just taking our data, applying a new cut to a new data set, change the normalization range of our exponential, and then create an ambient log likelihood on the right and minimize this. So now we're fitting the right tail. You see, minimizes means we're giving in the loss that should be minimized. That went pretty fast. So now we set our lambda, and we can fix that because we don't want to have it floating in the fit afterwards. And now we can just minimize everything, and afterwards just plot it. As you see here, fit converged, everything's nice, and this is our result. we can inspect our result further. So this is if you present the result, this is a whole overview, whether it is valid and conversion, everything. We can also just look at the parameters and they tell us the values and whether there are limits and so on. We can also access each of these components individually, or also extract some information about minimum and so on. To go on, we can try to get an idea of the uncertainties, which we can do with the hepstats method. This uses the iMinute implementation, but we also have, as you see, a zfit one, which is completely independent of the minimizer. And now we see as in the parameters, we get a new column here, shows the hepstats, and we can also do minus errors. A special thing is that new result is returned. This is if a new minimum would be found. And if you have that, then we'll also get our errors out. One simple thing that we can do, as we see here, get now the minus errors, is, for example, to do a profile plot, which maybe seems difficult, but if you look at that, all we do is we fix one of the values, for example, signal yield, then set the values and just append the value of the loss. And then we get a profile plot. Last one of these, we also get stuff like the covering.
Jonas,
yes?
Sorry to jump in. I think, can you maybe slow down a little bit? We're getting a few comments and a few requests for you to take it a bit slower.
Okay, sure.
Okay.
Sure.
Thanks.
Okay, this is so far the end of zfit. And this is where now hepstats would come in. But we'll stay with zfit and look at another example where we see the whole parts that we'll go through again. Which is this one here. So as I've told before, the whole zfit workflow is exactly the same all the time. You have these 5 parts, these 5 independent parts. What we've done before, we've loaded data, we've built a model, built a loss, and minimized it and got a fit result. And here we're basically gonna do the same thing again, just with a different model, with a different loss. And one thing that we will also do here is to add a constraint, which is basically an additional measurement. So this is basically about how can we combine measurements. And there are 2 ways. What we can do here again is create some data, just some signal and some background. We again here create our observable. And we load the data from NumPy. So we got our data object, we got again our observable, one-dimensional. And what we're doing here is we build a model. Here we build a Gaussian as our signal, a parameter, and the Gaussian. Here we build the background, which is an exponential, and lambda as a parameter. Then we get the yield for the signal, the yield for the background. We create both of them as extended. And then we create the sum again and get our final model here. Let's do that. This so far is basically the same as before. All we're doing is we build our model slightly different. So what we're going to do now is, instead of doing just a simple likelihood fit, we can add a constraint to it. This is, let's say, another observation that we had, and add this term to the likelihood. To add, for example, a Gaussian constraint, but we can also add arbitrary constraints. There is a class here. We can give our parameter, what's our observation, and the uncertainty of the observation. And now we do the same game as before again. We have our loss. It's an extended unbounded likelihood, and we have our model and our data. And what's different is we now also have a constraint term. We can also have several ones if we like to. And from here on, it's the same game again. We have a minimizer. We build again with minuit. We say again minimizer.minimize the loss. And we get our result. In the end, we can also do hesse on it. And we get, again, our result. As we see so far, this is all the same as before. We just slightly changed our model. We changed our constraints. Now, we use a constraint, which was small, so we do not fully see the effect here. We use the constraint, but what we could also do is to do a simultaneous fit. And a simultaneous fit is basically just a product of different likelihoods, or we can say the sum of negative log likelihoods. And this is done in zfit exactly in this manner. So if you want to have a simultaneous fit, which means we fit with one shape to one channel and with another shape to the other channel, and these models have some shared parameters, then we do it exactly like this. We just add the losses. So we gonna create some data here, just some fake data. And we do it again in the same. We create our resonant. Observable. Before we created the rare one. So that was just called PMAS. And now this is about like sharing parameters. This is pretty straightforward, I would say, in zfit, because every parameter is an object. So every parameter, if you have sigma from somewhere and you enter this in a model, then this is always shared because you're using the same sigma. If you're using different parameters, sigma 1 and sigma 2, then they're two different ones. Parameters themselves can also be a little bit more complicated. What we've seen so far are so-called independent parameters. These are the ones where we can directly change the value. But there are also dependent parameters, for example, compose parameters. And they depend on other parameters. They can be a sum, they can be a scale, but in general, they can be an arbitrary function of other objects, let's say. So what we can do here is we can say, instead of having two different sigma, we can say, okay, we have sigma as a parameter in our model before, and we have a scaling parameter, which takes values around 1. And then we create now a compose parameter. And this is done by giving it a function, which is this one here. And this is just the sigma times sigma scaling. And we have, of course, to tell them what is sigma and what is sigma scaling that this function should retrieve. And we do that here. We say the params are sigma and sigma scaling. So we're giving it sigma scaling. It remembers that, and when it's called, basically it calls this function and returns whatever is in there. So with this, we can now build our resonance model, which we do again with the Gaussian. What we do here is we use the same mu as we used in our other model. So the mu is shared. We have our sigma scaled here, and we use our resonant observable. We create again a background, an exponential. We create the yield, create again extended models. We do not have to create extended models, but that we get a yield as well. And we get our resonance model. Now, to do this equation of the simultaneous fit, we create our rare loss, as we know before, extended on with likelihood of the model and the data, the thing we created in the very beginning. Now we do the same for the resonant. We just take our resonant model and we take the resonant data. And to create a simultaneous fit, we just add the two negative log likelihoods. And now we get a simultaneous fit. Sorry, a simultaneous loss. And we can just give this in, minimize, and it's already done. We can also do some Hessian error estimation and get our results printed out.
Jonas?
Yes?
Quickly interrupting just to say that I don't know exactly how you want to share with Matthieu for hepstats, but you are just over half of your time now.
Yes, exactly. Yeah, he will take the last like 10-15 minutes. So we'll go on for like 5 more minutes or something.
No problem.
Thanks. So now we go for plotting, because plotting we need to do. And we can do this a little bit more fancy, as you see here, but this is just a nice plotting function. Actually, it looks way better. But to plot a simultaneous fit, it's very easy. It's done here. So what we do is we have our simultaneous loss, and this just contains now multiple models and multiple data. So all we do is we iterate through and plot each of them. I mean, they're independent fits. They're like, we can just take one model, one data, and plot that, and we take the other model and the other data, and we plot that. And here we see our nice fit was done simultaneously. So, and this is again when we're at the end of zfit, and afterwards we will hear more on what hepstat can do on that. Now you can also look through the notebooks to give everything. We added more content that we can do in the talk. There is also, if you're interested in doing toys, there is a very nice small example notebook. What we'll look at here in brief is the custom models. As mentioned, model building is a strong ability of zfit, and especially building custom models. So building a simple custom model is quite easy to do. This is all it needs. We can just specify our parameters that we want. We can enter it from setPDF, and we get an unnormalized PDF here. And then we can use this like any PDF before. We do the same game again. We get an observable, we create our parameter. We can also shortcut create a constant parameter if you just give in a Python number. This is all mixed with Python. And now we got our PDF. All right, the PDF we built here, this is just a simple polynomial, as we see. Nothing fancy. And we have it fully functional. Integral, sample, probability, always there, PDF. And this is done because everything like integration and sampling, we can do analytically, but it has a numerical fallback. So it just uses numerical method here to perform these things. And what we can do as well is to register an integral to add this. This is though not so interesting. What's more relevant actually is multiple dimensions and the real world example that you see where this can go. So this is the last piece of zfit that I will look at, which is an example of an angular PDF. Now, if you want to implement it for real, something, this is a shape that it's an angular observable from B to K star LL decay. And this is taken literally from a paper. It's three-dimensional, which we can say here. It takes all these parameters. You find all these examples online, so you can just look at them. And then we get the whole shape from the paper, which is nothing too common. I mean, just in square roots and everything in there. And then we get already our PDF. And with this, we can now do sensitivity studies. We can use this for anything. It's important if you want to create now an object of that, we now have a three-dimensional PDF. To create a multi-dimensional PDF, or let's say an observable for that, we need a three-dimensional observable. But this we just do again, we create three one-dimensional ones, like this one, like this one, like this one, and then we just multiply it. Because they're different, then of course the angular observables in the end is just three-dimensional one. We can also just use dictionaries to manage so many parameters. We don't need some extra method, that's all there. And we can now create here the angular PDF. We give in our parameters, and we give in our observables, and we have it. And again, as before, We can do the integral, we can sample from a three-dimensional PDF and get everything. And actually what we could also do now, because we have three angular observables now that we defined, and remember before when we created our small custom PDF that was in a different observable, the poly, we can just make this a four-dimensional PDF by multiplying it by the PDF that we had before. Since the observables do not overlap, this just creates a four-dimensional PDF. As we see here, the angular observables and the poly 2 observables. And if you have the product of those two that we built here, we get four observables. For example, the mass or something. That's it from my side. And now Matthieu will continue to tell you how you can do inference with all these models and all these losses built from zfit with hepstats.
Thank you, Jonas, for the zfit introduction. Do you see the notebook?
Yeah, that's good.
Cool. So just go back to the previous notebook where Jonas left us with a simultaneous model with the B mass and a B mass resonant mode. So we saw that we observe some signal, and now we would like to, for instance, quantify how significant is this excess. So to do so, we can do an hypothesis test, and we can do that with hepstats. So just putting back the value we got for the signal yield in that channel, we see that we get 140, 30 plus or minus 20. And we want to compute the significance of this excess. So we will do an hypothesis test, and in a hypothesis test, you have to define a null and alternative hypothesis. So the null hypothesis is a background-only hypothesis, so the signal yield equal to 0, and the alternative hypothesis is the signal yield equal to the value we found with a fit. In hepstats, to formulate a hypothesis, you have to use POY classes, stands for parameter of interest, which works like this. So it takes as input the zfit parameter, the signal yield, and a value. So this means when this POY will be used wherever in hepstats, it will say apply this value to this parameter. Just note that here we don't define the alternative hypothesis, because by default, for now, it is taken as the best fit value for the parameter. For the test statistic that we use, that is used in hepstat for the to do the hypothesis test, is a profile likelihood ratio defined like this. So a ratio of the likelihood for the null hypothesis and the alternative hypothesis, where here the theta hat is the value of the nuisance taken from the fit, and theta hat is the values of the nuisance parameter when the signal is set to 0. Then you can compute the p-value, which is the integral of the test distribution under the null hypothesis, from the observed value of the test statistic in our data. So with this p-value, we will assert whether we can reject or not our null hypothesis. In hepstat, the test statistic and the p-value computation is done in a calculator object. In this example, I will use the asymptotic calculator, which assumes that this test statistic follows a chi-square distribution, which simplifies the p-value computation just to that. So 1 minus the CDF of a Gaussian of the square root of the observed test statistics. So this is done like this. So what we need is, for the calculator, the loss, because we need it for the test statistics. So we just use the previously defined loss, NLS minimums, and a minimizer to eventually compute, for instance, the value of the loss, the minimum of the loss, for the null hypothesis. Then you can set as argument attribute the best fit, the previous result found from the fit, which just in order to avoid to compute again the likelihood with all the parameter free, so the best fit. Equivalently, you can actually just give directly the result as input, because the loss is, you can find the loss, the model, and the value inside the result. In hepstats, there is another calculator called the frequencies calculator, which actually construct the test statistic distribution with pseudo experiment, but for the sake of time, I don't show it here because it takes a lot of time. Then to actually compute the p-value and then the significance of the observation, there is a high-level class in hepstats called discovery, which takes as inputs the calculator and the POI for the null hypothesis, which will basically ask the calculator to compute the p-value, and then the discovery instance will compute the p-value into a significance like this. So let's see. Okay, so for our particular case.
Matthieu, sorry to cut in. You've got 5 more minutes really before we should finish, and you do have quite a few questions. So I will be good to move on to.
So we get a p-value of minus 13, which is a significance of 7. So well above the 5 sigma threshold for discovery. So we can assert that this is a genuine cilia. We are happy. Now let's try to compute the same with the same example, but with a lower number of signals. I won't go in full detail to that part. It's very zfit specific, but just a few words. I just sample new data from the model that we fit by setting here the yield to 10. And now I'm just recomputing a new calculator and a new discovery and a new p-value. So here it's actually, since I don't give the best fit to the calculator, it actually does the fit inside. And we see that we get this time a very low significance, because we find we fit a signal yield of 2. So we might actually consider instead to do an upper limit. So I won't go through the detail to the test for the upper limit. You just use a different test statistic, and we, for a given value of the signal yield, we can compute a p-value for a given hypothesis of the signal yield. And what the upper limit class, a new class, does is to actually compute the value of the p-value as a function of anything and try to find the value for which the p-value is equal to 1 minus alpha, the confidence level, typically 95% confidence level. So here, I just go quick there. So we give, as before, to the upper limit a calculator, but then we also give a scan range for the value of the signal yield, where we want to evaluate this p-value. And we also need a background-only hypothesis for the expected limit. So this is the result. We get an observed limit of 33. And this is here a graphical visualization of how the scan is done of the p-value as a value of the signal yield. And we see that this is where the line with the red dot and the red line cross, that is the upper limit. So now, different topic. I will talk about the S-plot technique, which is also implemented in hepstats, which you might want to need S-plot where you have a data sample with several variables populated by different sources of event and background, of events like signal and background. And you want, in some of the variables, for instance, unfold the signal distribution. So here I generate a data sample of 2 variables of an invariant mass and a signal and a lifetime. I generate the mass distribution from the previous model, the resonant model, and I generate some signal here and the same number of events. I draw some event from an exponential distribution for the signal and a Gaussian distribution from the background. So we want actually extract from this the signal component. So splots needs for that a discriminant variable where you can easily model the signal and background. So for instance, here, we already did that before. We model the signal with a Gaussian and the background with an exponential. So splot will also need the yields. So to determine the yield, we need to do an extended maximum likelihood fit, which we do here. Up. So this is the result of the minimization. We found the yields, and we, just for sanity check, plot the projection. Now, splot with the yield and the signal PDF, and the PDF for each of the species, like the background and the signal. Now you can compute the so-called S-weight the following way for the background and the signal for each event. So you will compute, for example, for each event, whether it is more event signal-like or background-like. So you do that with splot hepstats with this function, where you give the model, extended model, and the data that you fitted.
Matthieu, sorry, but I think we've reached the time we should change, and I would like to give you a minute or two for one question at least, because so I know we started a little late. So,
okay,
can you very quickly?
Yeah, this is the last, exactly the last cell.
Okay.
So we got the S-weight for each of the species, so for the background and the signal, and now we can actually apply the weights to the lifetime distribution. Here we do a weighted histogram of the lifetime distribution, and we compare to the true distribution, and we see that it matches almost perfectly. And I'm done. Thank you very much. I don't know if Jonas.
Thank you very much. So I will, in the interest, I'll share. We had basically a bunch of questions which we'll copy over to Slack afterwards. But I'll take one question very quickly, which is: can you comment on what are the benefits to use zfit in comparison with other fit packages, e.g., roofit? Matthieu or Jonas, do you want to answer? If not, we can have.
So, yeah, there we go. Yeah, one thing maybe afterwards, later on, I have another talk on zfit where I have a little bit more time for questions and where we'll talk about all the changes that have been so far and so on. So if you don't get your question answered now, you can ask there as well. On the main benefits, I would say, is that roofit is a C++ library and will stay a C++ library, and zfit is a Python library. As you've seen, it is fully integrated into the Python ecosystem. You can use everything, numerical stuff. You can even directly use NumPy, as I will show later on, and everything. Also, writing a custom model, you just inherit, you implement your own function just the way you like it. You're all part of this thing, and you don't really lose anything in terms of speed or something against roofit. Sure, it's not as mature as roofit. There are some features simply missing, but it's way more comfortable to use. You don't get any segfold error if you try to build your model in a function and all these fancy stuff.
Presumably being on GPUs, there's a big difference in terms of what's differentiation, and the fact you can use a GPU quite conveniently, or is that not a big feature nowadays compared to it?
Well, yeah, that's true. You can, I mean, let's say there are many features actually. Also, that it's sometimes even faster for than roofit than in larger fits. You can use a GPU for free, like it just can automatically switch everything. You have multi-CPU port and so on. Yeah, I mean, there are many things, but I would say the main thing is it feels just good to work with, very easy and fully integrated into the Python ecosystem.
That's great. Thank you both very much. It was a really interesting and very thorough tutorial. I really want to play with it myself.